Hey class, I wanted to make a video to kind of talk through some of the concepts and problem solving strategy for this homework question, which is number 60 from chapter 4. So what we have here is interesting and kind of weird looking, but we have this clown who's going to do a little prank where he pulls down on a string and it knocks him over, tips him over, so that he ends up just kind of hanging there. So all we're given though is just two simple pieces of information. We're told that the clown has a weight of, in this case, 940 newtons, and that there's a coefficient of static friction between his feet and the ground equal to 0.560. And that's all. And we're asked to figure out what's the minimum force he needs to pull in order to cause himself to tip over. So there's a lot of different concepts at play here. The first is to recall, right, as he pulls down on the rope, he's going to be pulling with a force downward, right, on the rope, and that's going to generate tension in the rope. And since it's the same rope, it's going to be the same tension at all places in the rope. And so really the force that he's pulling on his feet will just be equal to the same tension force that he's pulling down on the rope. So that's the first key concept to sort of understand here, is that the tension will be uniform throughout this rope. So now we have to think about, all right, what's required for him to tip himself over? So as he pulls, that tension force from the rope is going to pull against the static force of friction. So let's maybe just go ahead and draw a free body diagram. I know some of us need more practice on free body diagrams, so here we go. Let's act like here's our clown, right? Or maybe even just to help us see it, let's kind of make him more like a stick figure, I guess. So here's our clown. He's got his hands up here, right? And then here's his body, and here's his feet at the ground. So that's the clown, okay? I don't know how to draw a clown, but there we go. All right. So let's think about the different forces acting on the clown here. So there's going to be, as he pulls down on the rope, the tension in the rope will be pulling up on him, Newton's third law, equal and opposite forces. So there's going to be the tension force as he pulls down will result in an upward pull force on him. Then he has gravity acting on him, so he has his weight pulling down towards the center of the earth. In addition to the tension force, there's also an upward pointing normal force from the ground pushing up on his feet. And then lastly, at his feet, we have the tension pulling again to the left, and opposing that is going to be the static force of friction. So when we try to figure out how hard you need to pull to tip him over, you can look at the forces in the x direction. Because if we notice, check it out, the tension force here is going to have to be opposite of the static force of friction, and the static force of friction is going to resist the tension as much as it can up to the maximum possible static force of friction, at which point, when the tension becomes larger than the static force of friction, his feet will begin to slip. So that's what needs to happen, is we need to overcome the maximum possible static force of friction in order to cause him to start to slip. So if we recall, the maximum possible static force of friction is going to be equal to the coefficient multiplied by the normal force. So at first glance, a lot of people will be like, oh, great, static force of friction, we just need to overcome that, coefficient times normal. Normal for something on a flat surface equals the weight, and so we're good. We'll just take 0.56, multiply it by 940, call it good. No, that's not correct, because check it out. As he pulls down on the rope pulls up on him, and so the normal force actually changes based on how hard he's pulling. And to prove that, we can use sum of the forces, right? If we do sum of the forces in the vertical direction, knowing that he's at equilibrium up until the point he starts slipping, right? Knowing that he's at equilibrium, we can see the tension plus the normal force minus his weight equals 0. So rearranging these, the normal force is going to be equal to the weight minus the tension. So if there's no tension force, then the normal just equals the weight. But since he's pulling down, that tension force will reduce his normal force, will offset some of the weight pushing down on the ground. And you can imagine this, right? If you're thinking about doing a pull-up and you weigh 940 newtons, if you pull on the bar 500 newtons, there's only 440 left to be supported by the ground, and so your normal force would only be 440 newtons. So what this means is that the normal force is going to change based on how hard he's pulling, and that's going to affect the force of friction. So just to go with the process, right, our general process is draw the free body diagram, do the sum of the forces to try to solve. So now that we've understood some of the concepts, we can do that. And in fact, we already did in the y direction. We know that the normal force equals the weight minus the tension, but we don't know what that tension is. Let's look at the forces in the x direction, which again, we already conceptually talked about, but we can see that the force of static friction minus the tension is just going to be equal to 0. And the reason I'm setting it equal to 0 and not ma is because we're looking at right before he starts slipping, the maximum force he can apply up until he begins to slip, and right at that kind of transition point is when he'll then begin slipping. And so that's why we're solving for those forces equal to 0. So what we can see then is that the tension force applied is just going to be equal to the force of static friction maximum, right? Because we're looking at how hard he has to pull to start falling. And since we know friction is coefficient times normal, we can say that the tension is going to be equal to the coefficient of static friction multiplied by the normal force. And now we don't know the normal force, but we can take and substitute in weight minus the tension for the normal force. So if we do that, I can come down here. I'm just moving things around to make more space. So my tension is going to be equal to the coefficient multiplied by weight minus tension. And so from there, it now just becomes algebra to where you can solve for the tension force. You can distribute your coefficient and rearrange things. I'm not going to solve this all the way for you all, but I believe you should be able to add this over to the other side and combine your different parts with t, divide, and solve. All right, so I'm going to leave it there for you. But again, just to remind you the process, right? We start by understanding what's going on in the problem, make a free body diagram to help us visualize what's going on in the problem, and start working through the sum of the forces. And in some cases, as we saw here, we have to use both x and y together to try to solve. I hope that helps. Keep me posted on any questions you'll have. Have a box-worthy day.